As was mentioned, my student Matthew Clark unfortunately decided he wanted to graduate and start a company to commercialize this work. So he's busy, but I'd like to explain a little bit of some of his thesis work. To start, currently from this Business Insider report, the drone industry or UAV industry, and there's a lot of terms in there, and I'll use them loosely throughout this presentation. But when I'm referring to drones or UAVs or quadcopters, I'm referring to these quadrotor systems, some multi-copters. But presently, it's about a $125 billion industry for all these UAVs. And if you look at this, interestingly, currently a large segment of that market is actually for infrastructure inspection. So in my lab, I'm a sensors guy at heart. I see drones really as a flying sensor platform. So it's a flying platform that enables us to put sensors in interesting places to solve interesting problems. And that's how I started bringing that in my lab. To kind of put this work into more context, last year DJI, the largest manufacturer of consumer drones, partnered with Ford Motor Company and the United Nations Development Program to create a developer challenge where they wanted to use DJI products, of course, to build autonomous flying robots that were able to take off from the back of a pickup truck, fly through an obstacle course very low using sensors to identify potential victims of some supposed natural disaster, and then land back on that moving pickup truck. And all this was done then using cameras and other sensors for active tracking. And through this project, there were several areas requiring innovation, and one of those was the necessity of terrain following. One of the challenges, if you look at most flight controllers, especially for consumer grade or low cost, is that they measure the above ground level altitude purely on the initial starting altitude when you turn on the system using GPS. And this works very well if you're in a small room or a flat surface, but if you live somewhere like Hong Kong or the Highlands of Scotland, quickly flying at level ground becomes an impact. And so there's very much a need to have an accurate measure of the actual altitude above ground so you can make corrections, especially if you're doing things like sensing or photogrammetry where your resolution depends on your altitude, so you'd like to keep that consistent. A lot of work's been done in this area, and two major areas of interest of competing thoughts. One is using map-based technologies, where if we have an accurate map, say from Google Earth, we can then use that information, our GPS coordinates, to modify our terrain to follow. One of the challenges with that is if you don't have an accurate map, that creates problems, and things like disasters where the map may have just changed because of large debris or that would render that problematic. Another area of intense research is vision-based navigation for terrain following, but unfortunately this is computationally intensive. And in the case of our application where we have one computer on board, limiting computational and battery power, we'd like to simplify that. So to solve this problem, the solution was to add more sensors, which I think is great for this audience. We evaluated two different sensors for AGL measurements in this work. The first is the DJI guidance system, which is up to 5 ultrasonic time-of-flight sensors, as well as some low-resolution stereo cameras for optical flow. And these are tied through a proprietary box with some inertial sensors that gives you about a 10 hertz data output rate with 5 centimeter resolution, and they advertise a range of 20 meters. One limit of this is that it has to be rigidly mounted on the frame for the system to work. Additionally, we decided to explore a discrete laser rangefinder from Lightware Optoelectronics in South Africa. And this is a very lightweight system, gives you about 20 hertz output data rate with centimeter level precision in 120 meters range. And additionally, it lets us measure over water, which opens up some interesting applications. For initial testing, these were mounted rigidly on the frame. So you can see here is the guidance system here, and here is a rigid mounting of our LiDAR system. To kind of give you a zoom out, I'm focusing on the sensors, but this is the whole drone. This is the platform we used throughout the work. It was a DJI Matrix C100. It has a diameter of about 1 meter. You can lift up to 5 kilograms. And we have then a Linux PC here running ROS that can do our vision processing and our control, GPS as well as all of our sensor packages. This is a nice big system. A meter is actually very large, and so for indoor testing, these rooms get very small, and so it kind of restricted us to a lot of simulation outdoor testing. The first thing they wanted to evaluate then was the performance of these sensors. You know, manufacturers love to advertise specs, and so what you can see here is in green you've got the GPS. If we just climbed to an altitude of 25 meters and then descended, and the laser tracks that very well, with very little noise. But what we did find with the guidance is it's quite noisy, and above 9 meters it cut out. And it didn't cut out gently, it just dropped out the data, which is not a smooth thing for navigation. And this was very repeatable and unfortunate, and well, that kind of pushed us in one direction. Another challenge when you look at quadrotors is when you're hovering, if you have a rigidly mounted sensor, it's aiming straight down. So we can directly then measure the altitude or the AGL. And this is commonly then used in even like very cheap drones now for landing and takeoff. But due to the dynamics of quadrotor flight, as you start moving in a forward direction or a lateral direction, there is an associated angle of pitch to enable you to move forward. What that means then is that the sensor then pitches in the opposite direction or pitches backwards. So that induces an error that is dependent on this forward velocity, as well as if you're trying to use this sensor for measuring the terrain that's coming up, you're looking in the wrong direction. So this is a challenge we need to overcome. To kind of evaluate the sensors for this and make the point, if you look here for the laser rangefinder, here is a plot of the pitch angle of the drone as it's moved around, and then the associated altitude here. And it moved around a lot. It's a little bit noisy, but what you see here is here's a nice curve that corresponds to the anticipated offset. When we did the same thing to the guidance, you'll see the GPS noise up here, but it appears that the guidance black box was making some corrections, but then you get large amounts of noise. And so this was undocumented in the literature and kind of added a little bit of frustration. So this really then pushed us to look at the laser rangefinder as a good solution for our problem. Overcoming this angle then, the solution was then to use a gimbal stabilization system. And this was a very low-cost gimbal originally designed for like GoPro action cameras. And that gives us at least 35 degrees in every direction for stabilization. As well as because it's a controllable gimbal for cameras, we can also control the angle and add offsets, which can be useful for control in other applications. And so you can see here then the sensor has been mounted on a nice 3D printed case and tucked underneath the drone. Just to demonstrate then the system in action, you'll see here then is the gimbal. Here's our primary camera system. We still have our guidance system up here. So that'll plug it in, and the thing stabilizes aiming downward. And now, no matter the orientation now, the control will keep that vertical. So we will always, no matter what the system is doing, we'll always have a downward facing measure of our ground, which is what we want. I always think it's fun to see this stuff. Flying robots. So another interesting thing we can do, because we can control it, is if we're looking straight down, that's great, we know what's right below us. But the reality of systems is that there is some reaction time. And so if we know or we can predict or estimate the reaction time to make a correction of a change in the altitude, we can then look forward based on our velocity by some distance so that when we see a change in our altitude, we have time to correct. Right? Otherwise, we come too late and we won't react in time. And so in this way, we can look for a detection point in the forward direction, which allows us to actually do high speed, or the goal would be high speed terrain mapping. And so that's something interesting with this approach. Once you have that in mind, if we're not on flat terrain, as shown by this cartoon of a simplified like hill, in Hong Kong everything's a hill, so we like to model it that way. Here you can see if in the case of you're looking forward, if there is a change in your z height, we can then compute that to a change in our z height and our path. And just to kind of demonstrate this in a cartoon, so if when our flight is initiated, we first take off and give the robot a goal. It then detects what's going on in front of it. If it detects a change in Z, it will then adjust the Z as it flies, and this repeats as quickly as we can, right? Now, depending on the data rate of our sensors and our velocity, this will have a low passing effect, but it does enable us to ultimately get to our target where we can maintain an altitude there. Now, I love throwing this out there. They see who's awake still. So this is the kind of the state machine of the whole system. And really, with robotics, there's a lot of other pieces that go in. So you can see here where we're feeding in our forward velocity and our reaction time as well as our target. And then we initialize the system. And then there is a loop here that's basically going and checking the Z. But additionally, we have to add some pieces for, say, obstacle avoidance. So when we run into something we can't go over, do we have to go left or right, or to go up and over it dramatically? And then also, can we kind of break this loop and add more navigational offsets? So when we get additional information from our systems, can we fix it? Testing this, a lot of testing was done in the simulator. Unfortunately, a lot of this work was done during typhoon season, but it works very well in our closed loop hardware in the loop simulation system in ROS. Additionally, trying to do some very small scale discrete testing on a ramp worked very well, although the students had a lot of trouble where the GPS error was such that often the robot would miss the ramp. So many trials, but some basic testing was done, and this is now being pushed further. So with that, I've introduced really a novel gimbal-mounted laser rangefinder, and a lot of sensors and rangefinders have been used, but the addition of the gimbal, I think, gives it some added advantages. We did compare the performance of these two sensors and found some limits that were, they pushed us in one direction, and really tested this in our simulated environment and start looking at using it in the real world towards our current goal of offshore wind turbine inspection. So with that, I'd like to thank, of course, my students who do all the hard work and got to fly the drone while I was in the lab writing proposals, and thank you for your attention.